So yesterday you learned how to solve projectile problems if they've been launched from an angle and they land at the same height that they were launched at. And today we're just going to add in projectiles that are launched at an angle but that land at different heights. So for example, something is launched off a building at an angle. Okay. We've done horizontally off a building, which there are different heights there. And we've done at an angle to the same height. So this kind of puts the two together. So you have the same basic assumptions as for the other types, but you just have to understand what's going on here. And so the main thing to realize is that if this were landing at the same height, then right here, like yesterday, this would be your max height, your Y max, and this angle and this angle would be the same. Right here at this top spot at Y max, your Y velocity is equal to 0. Your x velocity is the same throughout. The time over here is equal to the time over here. The distance over here is equal to the distance over here. All that's going on. But if they're going to different angles, essentially what you have is you have an angle launched problem to the middle, and then from the middle onward, you have a horizontally launched problem. So this kind of puts the two together. So we're going to make a chart for this as well, but it's going to be a little bit more complex. The chart is going to have the up portion all the way to the middle, and you'll have it broken down into X and Y. But then it's also going to have the down portion as well, and that'll be broken down into X and Y. So it's going to be a little bit more complicated. Let's go ahead and do a problem. Okay, so here is our example problem. A high-powered rifle fires a bullet toward a hill at an angle of 39 degrees with a velocity of 125 meters per second. The bullet lands on the hill 20 meters higher than the height it launched from. Find out everything you can about the bullet. So the max height, the range, the time in the air, the velocity that it launched, or excuse me, the velocity that it lands at, the angle it lands, everything you can think of. So I'm going to draw a little picture, just kind of, this is my, it's landing higher than what it launched. We said that this was 20 meters higher than what it launched at. So it's going to launch, and it's going to go and land right there. And we said this angle was 39 degrees with a launch velocity of 125 meters per second. The middle is somewhere in there. And we need to figure out everything. Okay, so max height, range, hang time, impact velocity, and impact angle. So the chart I'm going to make looks like this. We have VI, VF, AT, and displacement. We're going to find that for the X and the Y, just like before. But the difference is that we're going to have a second section to this chart. And the second section is also going to be finding an X and a Y. And this section here is on the up portion. So that part. And this section is on the down portion. So after it reaches its max height when it's on its way down. Okay, so the first thing we're going to do is figure out our angle and our x and y components of our velocity. So we have our 125 meter per second vector, and we need to break that down into the y portion, the x portion and the y portion. And so we're going to use, and that's a 39-degree angle. So we're going to, the y portion is over here. So that's our opposite, and the x portion is our adjacent. So by now you should know that you could find Vy, which is opposite, by doing the hypotenuse 125 times sine of theta, which is 39 degrees. And we can find V of x with the same thing, but it's the adjacent, so 125 cosine 39 degrees. And when you put that in your calculator, you get that V of y is 78.67 meters per second, and V of x is 97.14 meters per second. So my V of x is 97.14, and my Vy is 78.67. Now I know other stuff because this is a projectile problem. In the x direction, we know that the x doesn't change, so that stays there. 0 acceleration. We know that the acceleration in the y is negative 9.8. And this is going up to the max height. And so my final velocity in the y direction at the very tippy top is going to be 0. I also know that as this continues on, the x velocity doesn't change. So it'll be 97.14 in this up portion, but it'll also be 97.14 in the down portion. So I'll go ahead and put that in also. I'm going to do this in green, all of these calculations. And I'll finish the rest of those assumptions later, but again, our acceleration will be 0, and, well, I'll go ahead and put it in 0, and that'll be negative 9.8, etc. We'll figure the rest out. The next thing that we can do, so we have the 3 pieces of information we need that we can find time. So on the y side, we can do that time in the y direction is equal to Vf minus Vi over acceleration, which is equal to 0 minus 78.67 over negative 9.8, which gives us 8.03 seconds. So 8.03. Time is the same for both sides here. We're going to want the max height. We're also going to need the range. So we'll go ahead and solve for both the y and the x displacement. So for displacement on the y, that is VIT plus 1/2 AT squared. No part of this goes to 0. And so it's going to be 78.67 times my time of 8.03 plus 1/2 times negative 9.8, which is negative 4.9, times 8.03 squared, which when you solve all that through gives you 0.76 meters. And that is in the y direction. Now notice that I didn't get a negative value here, even though I put my negative in here. And that's because this isn't a negative value. Okay, we are going up. And so this is actually higher than where we were. We have a positive displacement. So that's 315 meters up. D in the x direction, that does have the 0, so we'll use the same equation, but this will go to 0, so we just have to do VIT, which means we just have to do 97.14 times 8.03, which gives us a displacement in the x direction of 780.03 meters. I'm just going to write 780 over here. Okay, so we have all of our information that we need for the up portion. So now we have to think about the down portion. I'm going to switch to green. So for this, we do know that the x is the same. That hasn't changed. Our acceleration in the x direction is still 0. Oop, I forgot my 1. And our acceleration in the y direction is negative 9.8. What we do know, so it's kind of like a horizontally launched problem. Right here, everything is now in the x direction. It was 0 y velocity at the top when it's at its max height. So now it's kind of like a horizontal. So our y initial for this portion is 0. We don't know the final y. But we also know something about the distance. We just have to think about it. So this distance here, the height was 316 meters. Now this said that it's going to land 20 meters higher than where it launched. So if we do 300, and I'm going to be more precise, 315.76 minus 20, that leaves us with 295.76 meters as this distance. This is not drawn to scale. So that's 296 meters. So that is my y. So it's going to fall that much. So it's going to fall negative 295.76 meters. And so now I have my 3 pieces of information. So to find my time in the y direction, okay, I'm going to use d is equal to VIT plus 1/2 AT squared. VIT goes away. I rearrange it, and I end up with the square root of 2d over a, which means the square root of 2 times my displacement is negative 295.76 over negative 9.8, which takes care of the negatives. And so then I end up with a time of 7.769 seconds. Notice that with a displacement in the y of 315 and it only landed 20 meters higher, that's almost as far. So it's going to have to fall almost as far as it went up, which means my time should be almost as much as my time up. And you see we went up with 8 and we're coming down at 7.76. So it's almost as much time. That'll be the same for the x and the y on the down. I can find my displacement in the x direction with VIT. Acceleration is 0, so that goes away. So velocity times time, 97.14 times 7.769 is equal to 754.7 meters. 754.7 meters. And then I can find my final velocity. VF is equal to VI plus AT. VI was 0, so that goes away. So I just have 9.8 times 7.769, negative 9.8. And that ends up being 76.136. 76.114 meters per second in the Y. So that's everything filled out on the chart. So we have everything that we need. The last thing we're going to find, because we know our max height, we can find our range from what we have, we can find our hang time. Let's find impact velocity. So impact velocity, it's coming in at the hill at this angle, but that has an X portion of 97.14, and it has a Y portion of 76.14. And so remember, this basically makes a right triangle. And so the square root of 97.14 squared plus 76.14 squared is going to be my velocity. And that gives me an impact velocity of 121.59 meters per second. The angle, theta, is equal to inverse tan of, the opposite is the Y portion. So inverse tan of 76.136 over 97.14, because it's opposite, which is the Y portion, over adjacent, which is the X portion. And that ends up giving us an angle of 38.1 degrees. And we can't really say north of east because we don't know if it was going north of east, but we can say it's 38.1 degrees above the horizon. We can say that. Or above the horizontal. Right. We don't really know what direction anything was going. We assume it was going east, but so here is our impact velocity and our impact angle. I'm going to erase this really quick. It's in my way. And so our impact velocity was 121.59. I'll just say 122 meters per second. And the angle that it was at was 38 degrees, or 38.1 degrees above the horizontal. Now for our max height, this was the lowest portion, that's the highest portion, so our max height was 316 meters. For range and hang time, for range, that is how far it went. So it went this in the up portion and this in the down portion. So range is equal to 780 plus 754.7, which gives us a range of 15 34.7. So we'll just say 1534, or maybe even 1530 if you want some semblance of significant figures, which I don't really care. And then the hang time is how much time it was in the air. So it was in the air for 8.03 and then 7.769. So when you add those together, you get 15.8 seconds. Okay, so I think I figured out everything we could come up with from that particular piece of information, of just the angle that it was shot at and the velocity and the fact that it landed a little bit higher than it was launched. Okay, so now you have everything you need to finish off the packet. I believe I said don't do number 3 and 4, or 4 and 5, whichever ones it was that I said don't do yesterday. Those are the ones that are like this. And now you have all the information you need and you can solve those as well. There are a couple of hard ones on there, and these do take a lot of time. But they are a little bit more complicated, but totally doable. Okay, so good luck. Finish your worksheet. It's going to be due on Friday.